Hello everyone, welcome to another video. In this video we're going to discuss what downstream resiliency is and what is the relationship between timeout, retry and circuit breaker with this downstream resiliency. Okay, so first of all, let's understand what downstream resiliency is. So let's imagine that you are developing your service. Okay, let's call this service A. And in the process, the service A needs to communicate with some other service. Okay, doesn't necessarily need to be on a microservice architecture. This can be a monolith communicating with, for example, a payment service, an external payment service, or something like that. Okay, but the point is you have a service and that service has to communicate with another service. Okay, for simplicity's sake, let's call this service B. Okay, now what normally happens is that this external service B sometimes needs to communicate with another service. Okay, let's call here service C. And the normal flow of calls should be service A calling service B and service B calling service C. Downstream part here means that we have a service of our own, which we call service A, and the service A has dependencies, okay, in this case directly service B. Okay, so a downstream dependency is a service, in this case service B, that is used by our current service, service A. Okay, and naturally service C is a downstream dependency of service B. Now where does the resiliency part comes in here? And we will see some examples in the next slides, but what happens if all of a sudden service C starts to fail? What will happen to service B? Okay, of course it's outside of our control, but we need to think about it. Now, in this case, for us specifically, what happens if service B starts to fail? Okay, how will our service A behave? Okay, so this is the resiliency part. How is our service A, prepared in an eventual scenario where failures in its downstream dependencies happen? Okay, and we will see some mechanisms, as I spoke previously. Timeouts, retries, and circuit breakers are normally used here. Okay, but this is a high-level overview of what downstream resiliency is in a nutshell. Okay, now we are going to see some problems that will arise when we have this kind of chain of dependencies in the downstream. Okay, now let's first have this scenario, which is very similar with the one we had before. So we have these three services. Okay, service A calls service B, and service B calls service C. Now what happens if service C starts to get slow? Okay, it's getting too many requests, as an example. Then, naturally, service B will also be slow. Okay, and then, of course, as we would expect, service A will get slow as well. Okay, now let's see another example, okay, of a problem that might exist. Okay, now again, service A calls service B calls service C, but instead of being slow, service C does not have any more capacity to answer any requests, to handle any requests, and just outright returns some bad responses, okay, as an example. Or it can be just 500 errors, for example. Okay, then service C just outright returns an error response to service B, and then service B returns also a bad response. Can be a gracefully handled response, okay, but anyway, the error is also propagated to service A. Now, what you could see based on these two examples is that any problems that arise on our downstream dependencies, they are propagated to our service, okay, to our upstream here, okay? And this is the main problem, that if you don't do anything, this is what's going to happen naturally, okay? Errors in the downstream services will propagate to your service, okay? And this is where strategies like timeouts, retries, and circuit breaker come in handy, okay? Because they allow you to somehow protect yourself from those problems, okay? Let's start out with timeouts, okay? So, just for simplicity's sake, I've removed service C, okay? But you can quickly understand how that would come about, okay? But let's just say my service A calls a service B and that's it, okay? Now, my service A calls service B, okay? And my service B is slow. Now, what can my service A do? My service A can say, hey, I don't want to wait forever for your response. I need to get an answer from this service in X amount of time. And this is where the timeout comes into place. A timeout is just a period of time after you send in a request that you are expecting a response back. And after that amount of time, if nothing comes back to you, you just assume you'll never get the response back and you move on with your life. Okay? So you can just assume that I'm not going to get anything back from this service and that's it. Okay? So I don't care whatever you sent to me. I just timed out. Okay? I don't care about you anymore. Okay? Now, if there are no timeouts defined, this operation here can last theoretically forever, okay? And the problem with this approach is that our service A would have resources hanged around for theoretically forever, okay? And this problem would lead us on service A to have some kind of resource leaking, okay? I have resources here pending on a response from service B, while service B is just slow, okay? And then a timeout solves this out, okay? Because if you don't send me a response in X amount of time, I can just free up my resources and life goes on because I'm not expecting you to send me something, okay? Now, today in modern frameworks like .NET, okay, our HTTP clients, they normally have timeouts implemented by default. Okay, in case of .NET, the HTTP client I think has a default timeout of 100 seconds. I'm sure in your programming language there must be some kind of default implemented. Okay, but anyway, timeouts are very important in this case. Okay, one of the problems with timeouts, and this is something we need to be very careful, is that we might ask ourselves, what is the correct value of a timeout? Okay, if I have to define a timeout, what is the correct value? Because big timeouts might be a problem because you would have your resources here hanged around for a little while, not doing anything, just waiting for a response. Okay, which is similar to what the problem is if you don't have any timeouts, okay? But the problem if you have a very low timeout is that you just ignore that this guy will never return you anything back and you just keep on erroring. And then if you implement retries, which we will see in a second, you are just keep on retrying for an answer. Okay, so if your value is too slow, you might put yourself too low. Sorry, if your value is too low, you might put yourself in a position where you assume that you will never get an answer from anyone, even though theoretically this service is up and running and can serve you quite fast. Okay, so there's a bit of a situation here that very high values are a bit of a resource waste. Very low values of timeouts might put you in a situation where you keep on retrying, or you keep on assuming no one will answer you, and then your platform might behave, weirdly. And so it's a dancing game we need to have in consideration. Now you might also ask yourselves, but how can I define this value? Okay, and this is where good observability comes into play. Okay, so if you have observability on your system, okay, you can see normally how in a good scenario how much time these requests take, and then you can put a little buffer in the in the higher level. Okay, let's assume that this takes normally 150 milliseconds. You can put it as 250 milliseconds as a timeout, give it a little buffer, and then you can have a very good timeout defined. So you can either do this in a trial, so you just randomly put values and test, or you can have, as I said, observability in place, and this observability will make you have more educated guesses. Okay, now let's talk about retries. Okay, again we have our service A. It has a downstream dependency on service B, and our service A just calls service B. Okay, now what happens if service B is slow? Okay, it's just not returning any response, okay, or might even return a error. Okay, we will speak about this in a second, but the point is that I try to ask something from service B, but it's not returning to me anything. Okay, what I can do is try again. Hey service B, what about now? Can you do something for me? And again service B just quietly doesn't tell us anything, and then we, as service A, we just call him again and say, hey, what about now? Okay, now this is a retry. Okay, you keep on calling the service if you don't get anything back, or if you get some kind of transient error. Okay, the important thing about retries is that the expectation of a retry is that it will eventually be successful, because we assume that the errors that service B is having right now are just transient, okay, just temporary. Okay, in circuit breaker we will see why circuit breaker is useful for other types of errors other than this kind of more transient errors. Okay, because here, as I said, service B might just be a bit overwhelmed, and not necessarily out of error, but just a bit slow because it's getting too many requests. Okay, and so we as service A need to be sensitive about this and try to understand how can we ask service B again for a response and not make service B even worse. Okay, now let's see, as I said, how we can ask, or on which amount of time should I ask again for service B. Because if I keep on asking every second, or doesn't matter the interval, but if I keep on asking every time, then service B might get just overwhelmed by my requests. Okay, it's the same as if you are a mail delivery guy or someone that wants to deliver something into someone's house. You go there, you knock once, okay, you wait a bit of time, and then you ask again. But if you keep on knocking consistently, you will not get any results, or bad results. Okay, so we also need to have this kind of attention with our downstream services as well. We don't want to make things worse, okay? Now, because of this, there are strategies as far as how spaced these retries should be, okay, in order to avoid this service that I depend on to not be overwhelmed by me, okay? But before we go and see those strategies, the strategies we can apply, there's one question that might be on your mind, which is how can I detect that service B is not okay and it's something that it's worthwhile a retry? So as I said before, or at least hinted at, is that normally timeouts are very used with retries. So for example, you do your first request, service B is a bit slow, and then your first attempt timed out. Okay. Another thing that is normally used as an indication that service B is going through some transient error and therefore worthwhile of a retry is based on the kind of HTTP status code that you get from the response, if any, from service B. Let's assume you get a response from service B. If you have a 408, which is request timeout, or 429, too many requests, or some kind of 500 errors, okay, those are status codes that normally you can retry because they indicate, okay, the service is a bit overwhelmed right now. If you retry, you might be successful. But there are other HTTP status codes that might not be worthwhile a retry. For example, a 401 or a 403. Okay, if you keep on retrying, you'll keep on getting the same error. Okay, there's nothing a retry can do for you there. Okay. Normally you can also do something interesting, which is if you own these services, or if your partner service or the service you are using has this kind of thing, which is normally you can have a retry header, okay, retry after header that can be returned on a response, and then this retry after header can indicate service say, okay, I can retry after X amount of time. If this service explicitly tells me that, hey, retry after X, okay? Now let's see the strategies, okay? Now the first one is retry interval constant, okay? By the name you can guess that you retry after, always after the same amount of time, okay? Let's see. Now I do my first request. I see that service B is slow, for example, timeout. I retry after 1 second, okay? Still nothing from service B, that's okay. I retry after 1 second, okay? So this is the constant interval, okay? Then you have the linear interval, okay? Again, you do your request, your first request. You see that service B is slow. You can measure this, okay? Timeout, for example. You try after 1 second, okay? This is your first retry. 1 second, okay? Then, okay, service B is still slow, doesn't return a response back to me. That's okay. I try after 2 seconds. Let's assume after 2 seconds you don't get any response back. You try after 3 seconds and so on. Okay? So this is the linear interval, okay? In this case, the amount of time we wait is the same as the number of the retry. Okay, but you can put it as the double, okay, 2 times 1, 2 times this, and then it still is linear, okay? Now, exponential backoff, okay? Again, same scenario. Service A calls service B. It detects that service B is slow. I retry after 2 seconds, okay? I detect that service B is still slow. I retry after 4 seconds, okay? And if service B is not responding back to me, I'll retry after 8 seconds, okay, on my retry number 3. Now, here you need to understand some mathematics. Okay, an exponential, okay, in this case is a power of 2 exponential, okay, is 2 to the power of something, okay? And that something that we are powering is the retry number, okay? So here is 2 to the power of 1, which is 2. Here is 2 to the power of 2, which is 4. Here, in the third attempt, if any, would be 2 to the power of 3, which is 8, and so on. This is a contrast with the linear approach, because the linear approach, you might have 2 times 1, 2 times 2, or 3 times 1, 3 times 2, depending on what multiplying factor, if any, you want to use. Okay? By default, we know that multiplication is 1, but nevertheless, okay? Here we are going to the power of, not exponential. Therefore, you need to understand how exponential works, okay? Now, there's an alternative to this exponential backoff, or let's say more an improvement, and we will understand why this improvement comes about, which is the exponential backoff with jitter, okay? So again, service A calls service B. We detect that service B is slow, but instead of just 2 to the power of 2, it's 2 to the power of something, sorry. We add to that value some kind of randomized number, okay? Here is 2 to the power of 1, which is 2, plus this 2 which was randomly generated, okay? So you need to randomly generate this jitter, okay? So on our second retry, we know that 2 to the power of 2 is 4 plus some random value, okay, that we can generate. In this case, the random value we generated was 7, okay, based on our code, okay? Then let's assume we had a retry number 3. We know that 2 to the power of 3 is 8 plus some random value we can generate, okay? Your programming languages should have a math.random of some kind, and every time you generate the next retry, you will do 2 to the power of n, where n is the retry attempt number, plus an auto-generated random value here, okay? Now, you might ask ourselves, okay? We might ask ourselves, why all of these approaches and which ones should I use, okay? So, my suggestion is always use this one, the exponential backoff with jitter, okay? The reason why is the following, okay? Let's assume that this service P is used by a bunch of other services, okay? So we have here, instead of service A, we have service A plus 1,000 plus services, I don't know. But we have lots of services here, okay? Now, all of these approaches we've seen previously, they are constant at the end of the time, except for this one, because in this one, we added some random number. And what's the problem, you might ask, of having that thing as a constant? Now, as I said, let's assume we have these thousands of services in parallel. Now, imagine if they are all by some random, it's random. Let's assume that by a chance of nature, they all do the retries at the same time. So they all do the calls to service, the first call to service B at the same time. Then that's okay. They detect that there's a timeout and they do this constant retries, okay? Because you don't have this random factor, you get the chance to overwhelm service B and therefore eliminate any benefits of what a retry gives you. The purpose of a retry is that you expect, there's an expectation of an eventual successful return, okay? Because we assume that service B is going through some transient problem. Now, if every parallel service now all of a sudden wakes up at the same time and goes to service B and just powers it with requests, so then service B will become a bottleneck and will be slow. And therefore, a retry doesn't serve any purpose because service B will always get hammered with requests. Okay? This is why exponential backoff with jitter, okay, anything that involves something random is very useful, because now if you have lots of parallel services, the chance for collision is smaller because you have this random factor here. And therefore service B can perform a little bit better. Okay? So whenever you are making this decision, beware that everything is a trade-off. Okay? In theory, it shouldn't be very hard to use any of these algorithms I just told you about. They are, in my opinion, straightforward. But keep in mind that all of them have pros and cons in terms of what happens if all services out of nowhere, they just wake up and use the same amount of time for retries and so on. Okay, you can have this risk as well. Okay, and having things randomized, this kind of randomized here helps you by ensuring that, okay, whatever downstream dependencies I have, okay, it can withstand my requests. Okay, so you will see on the industry and you will see on the articles about this that most people tend to go with the jitter one, okay, because you tend not to overwhelm the downstream dependencies. Even more important, sometimes these downstream dependencies, they are rate limited as well. So they don't allow you to just keep on hammering their services, okay? And so having a more spaced in time retry, like the exponential backoff, for example, allows you to space out your requests even more compared to a linear approach or a constant approach, okay? So overall, regardless of the algorithm you choose, the underlying thing you need to have in mind is how, with the retry, I don't overwhelm my downstream service, okay? Choose an algorithm that is spaced in time that doesn't cause problems on the downstream services, okay? One problem that happens with retries is this retry amplification here, okay? Now here is just some diagram I did in another tool, okay? It was easier for me to draw this, but nevertheless we come to the three services problem here, okay? Service A, service B, service C, okay? Now imagine service A calls service B calls service C, and now C is slow. Then B, if it has some retry policies, will keep on hammering service C, okay? In the meanwhile, service A detects that service B didn't provide him a response and therefore will retry again the same request. Then service B again will retry, call service C is slow, and then we'll do the retry. So as you can imagine here, depending on how long this dependency chain is, you can be in a situation where you will overload the dependencies with lots of retries. Okay, so be aware that if this is something that you control, let's assume these are services that you are developing internally. Okay, you have assume a microservice A that calls a microservice B that calls a microservice C, and C can even call D, for example. Be aware that you can have this scenario. Okay. Now, how can you avoid this? Can be tricky, but one thing you can do is just do a retry on this level and fail fast on the other ones. Okay, so pretty much put in place, should I do a retry or not? Because if I keep on retrying like crazy, I will have this situation keep getting worse depending on how long this dependency chain is. Okay, now let's see another pattern called circuit breaker. Okay, now circuit breaker is actually a pattern that is used in the electronics field. Okay, we just imported it back to software. Okay, and how does this work? Okay, first of all, let's understand when to use this pattern. Okay, so as I told you before, a retry is normally used when you are expecting that eventually you will get a successful response. Okay, because you assume that your downstream dependency is going through some transient problem. Now, with the circuit breaker here, circuit breaker is normally used for scenarios where you don't have this kind of transient problems. As an example, your service is down. Okay, now, no matter how many retries you do, your service is down, and that's it. Okay. Now, so this is the most important thing. Okay, so the circuit breaker is used for normally non-transient problems. Okay. And retries are normally for transient problems. Okay, that's at least my opinion on the subject. Okay, you might find out different opinions, but nevertheless, let's see how this works. Okay, so the circuit breaker has 3 states. Okay, closed, open, and half open. Okay, we will go to each in detail in a second, but let's first understand, just as an example, okay, the scenario we had before. Okay, service A calling service B. If everything is running smoothly, meaning that, okay, service A is calling service B and getting answers back, everything fine. According to circuit breaker, this is the closed state. Okay, meaning that everything is flowing and everything is running smoothly. Okay, but now let's assume that for some reason service B starts to fail. Okay, we can assume it went bananas and it's out of air. Okay, one thing you do with the circuit breaker pattern is that you normally define how many failures, how many requests can fail before you move from this closed state to this open state. Example, we know that service A calls service B, and on the circuit breaker I can say, okay, I can tolerate 3 failures. I do 3 requests to service B, and if service B doesn't return any successful response after those 3 requests, these are 3 failures, and I assume that service B nowhere to be seen, and I move my circuit to a state called open. Okay, as you can see here is red, which means that it's not okay. Now, we saw lots of concepts here. Okay, so the first and one of the most important is you need to define how many requests can fail in order for you to enable your panic mode. Okay, So service A calls service B. I can tolerate up to 3 failed requests. If I don't get any successful response from service B, I turn on my alarms, because for me service B is not up and running. And so I turn on my circuit to open. Okay? An open circuit means that communication between service A and service B is not okay. Okay, so I will not forward any more requests to service B. I will automatically reject. If someone asks me to call service B, I will automatically reject. I will not even call service B. I will just outright just flashing no, I will not call service B, because for me service B is out. Okay, so when a service is on an open state, okay, when the circuit is on the open state, service A doesn't even call service B. It outright rejects calling that service. Okay? Now, another important thing to understand about this open is that you normally define for how long do you want to keep the circuit open. Okay? For example, I can have this open for 5 seconds, 10 seconds, and so on. So you define for how long you want your requests to not be forwarded to the service, meaning that your circuit is open. Okay, so let's assume that you have configured your service to be opened for 10 seconds. This means that any request that is done to service A that needs to be forwarded to service B within that 10-second period will be automatically failed or rejected. Okay, so because service A within that 10 seconds time span will not call service B. Okay, so very important to understand this. Okay, now what happens after those 10 seconds? Okay, after those 10 seconds, whenever service A gets a request on which he needs to call service B, you will move your circuit from open to half open. Okay, and then try to call service B. Okay, so an half open state just means that I am going to see if I can have something from service B. Okay, I will not outright reject you. Let me see if he is okay now. Now you call service B. If service B is up and running and returns you a successful response, you move your state to closed. Okay, meaning that, okay, I can now assume that service B is up and running, is okay, I'm happy, and life goes on. Okay. Now, if I detect that service B is still returning me error messages, I just move my state back to open, and I stay here on open for 10 seconds, okay, depending on what time you have defined, and so on. And then after 10 seconds, whenever someone tries to request service B from service A, then you go to half open, and then if it's successful, you move to closed, and so on. So pretty much this is behind the scenes, you can think of this as a state machine. Okay, you have 3 states, which is closed, open, and half open. And these arrows here represent the state changes. Okay, so I can go from half open to closed, but never can I come from closed to half open. Okay, so this is a unidirectional arrow, meaning that just a state change can only happen from this to this and not the other way around. Okay. So closed can only come to open, open can come to half open, and half open to open, and half open to closed. Okay. This is a bit tricky to explain because it's it's a very sometimes very abstract. But let's try to sum this circuit breaker once again just to make it clearer, okay? Okay, let's try to see this again with our example from service A and B. Okay, so service A calling service B. Now let's assume that everything on this stage goes well. Okay, so service A calls service B is returning everything fine. So I can call again service B to do other operations, and then everything is running smoothly and everything is well. Now, according to our state machine here, our circuit breaker diagram, this corresponds to the closed state. So requests are flowing in, successful responses are being provided back, and everything runs smoothly. Okay. Now let's assume that our service is still on the closed state. Our circuit is still on the closed state, but service A now when calling service B gets errors. Okay, so I got an error. I tried to call it again, and I have another error. Okay. Now, as you remember from our diagram, we can tolerate up to X failures, okay? And after that X failures have been surpassed, our state machine changes from closed to open, okay? And will remain on the open state for X amount of time, where X is the amount of time you configure for your circuit to be opened. Okay, so as you saw here, I don't tolerate much failure, so at the second failure I got, that's it for me. I assume service B is out of air, and I moved from closed to open. Now let's assume that my circuit is going to be open for 10 seconds. Okay. Now, as I told you before, if someone within that 10-second period calls service A, and service A has to call service B, service A will not call service B. It will outright reject calling service B, because for him, service A, I don't care about service B for 10 seconds. For me, it's out. I don't even want to bother it. Okay, so it outright does not call service B. Now, after those 10 seconds, we now go into a more interesting position. Okay, I'm still on my open state, as you guys know, after 10 seconds. But let's imagine someone calls service A. Now, because it's over the 10 seconds, service A can retry, can just do a peek and see if service B is up and running. Now, according to our state diagram, this equivalates not to the open state, but to the half open state. So whenever we try to do this call first, we need to first move to the half open state and then retry the request. Okay? Now, to which final state we are going to move from half open or to either open or close depends on what kind of response we will get back from service B. If that response is a failure, then we are going to move to the open state, stay there for X amount of time, example 10 seconds, and then repeat the flow we are seeing here. But if this response is successful, then I moved from half open to closed. Okay, if it is successful. If it's not successful, as I told you, instead of closed, we would move to open and then follow every step we've seen so far until here. Okay, so again, moving to half open, and if it's successful, move to closed. If not, move to open again, and then you would then do all of this dance around again. Okay. Now these are the concepts that I wanted to pass to you on this video. I hope you have liked what we have covered here. Thank you so much for your attention, and I'll see you in the next one.